Here we introduce a new vocabulary word, and that is linear momentum. In the physics definition, it is very simple. All it is the product of an object's mass and its linear velocity. Oftentimes, we just talk about momentum, but linear momentum serves to differentiate linear momentum from angular momentum, which we'll talk about in Chapter 11. But for now, linear momentum, like I said, is just the product of mass and velocity. Velocity, of course, is a vector. Mass is a scalar. So our direction of our momentum vector will always be in the same direction as the velocity vector. And the units of mass is kilograms. The units of velocity is meters per second. So the units of momentum then is kilogram meters per second. There is no other name for it. Why the letter P for linear momentum? Well, Newton's second law was originally spoken of in terms of a change in momentum being caused by a force. Today we say, F equals ma. A force causes an acceleration. But originally, a force caused a change in momentum. And at that time, the time when Newton published his work Principia, there was a word impetus. And that was the quality of an object that was moved to be moving independent of an observed force. So from the word impetus, we get the letter P for momentum. Which has more momentum? A 40,000 kilogram truck moving at 2.2 miles per hour, or a 2,000 kilogram SUV moving at 45 miles per hour? The answer is they have the same momentum. Their mass times their velocity in meters per second, I've done the conversion here and here, shows me that they both have 40,000 kilogram meters per second worth of momentum. So heavy things and light things can have the same momentum because velocity is also a factor. A very large ship sitting still in the water has no momentum, whereas a very small object, a bullet, moving at a very high velocity, has a lot of momentum.
The momentum of any particle-like body cannot change unless a net external force changes it. For example, we could push on a body, in this case a little shopping cart, to change its momentum. More dramatically, we could arrange for the body to collide with a baseball bat. In such a collision or crash, the external force on the body is brief, has large magnitude, and suddenly changes the body's momentum. Let's consider a simple collision between a ball and a bat. The collision is brief, and the ball experiences a force that is great enough to slow it, stop it, or even reverse its motion. The ball experiences a force as a function of time that varies during the collision and changes the linear momentum of the ball. Let's look at this in closer detail.
Let's look at a collision between a baseball and a bat. Here we'll show it in slow motion first. There you saw the ball hit the bat. Let's go watch it again, and I'll just step through it frame by frame. You can see as the ball begins to be hit by the bat, the ball begins to compress and squish. And then as it leaves the bat, it returns to its regular shape. So the force acting on the ball throughout that time is not a constant force. It is changing. And in fact, let's look at it with the graph of force and time set next to it. So up here, we'll watch the video of the ball hitting the bat. Here will be the force on the ball from the bat as time goes on. Okay, let's look at that again, and we'll step through it frame by frame. Here we go. So before the ball hits the bat, of course, the force acting on the ball is 0. And as the ball first makes contact with the bat, that's when we see the force on the ball is beginning to increase. And as the ball deforms more and more, the force on the ball increases until at the maximum deformity of the ball, we see a maximum force exerted on the ball by the bat. And then as the ball begins to leave the bat and the deformity of the ball becomes less, the force acting on the ball decreases until, of course, it leaves the bat altogether, and that's when the force on the ball returns to zero. So let's look at an example. Here is a car traveling at 55 miles per hour, or 25 meters per second. Its mass is 1,000 kilograms, and it puts on its brakes, and it comes to a stop. So its final velocity is zero, so its final momentum is zero. So its change in momentum, or its impulse, is the final momentum minus the initial momentum, a change of negative 25,000 kilogram meters per second. Now let's take that same situation, a 1,000 kilogram car traveling at 55 miles per hour, and let's smash it into a wall. The end result is the same. The final velocity is zero. The final momentum is zero. So the 0 minus 25,000 is still a change in momentum of negative 25,000 kilogram meters per second. Both instances have the same impulse. Now you say to yourself, these situations are very different. And that is true. They are very different. In this one, you walk away to drive another day. Here, you're on your way to the hospital in the ambulance. But still, the definition of impulse is the change in momentum, and both of these situations have the same impulse. To show that in a simpler way, let's look at our equation for Newton's second law in its original form that said force is equal to the time rate of change of momentum, but that's the same as the change in momentum over the change in time. So let's cross-multiply delta t to the other side, and let's rewrite change in momentum as final momentum minus initial momentum. The mass is not changing, so we can factor that out, and we can just call this mass times change in velocity. So we see here that a change in momentum, if we assume the change in the momentum for any situation is a given, this right side of the equation will stay constant. But what can be different in different situations is the amount of force and the time interval over which that force acts. So we can have a very short time with a large force can produce the same result as a much smaller force over a longer period of time. This is quite evident with the use of airbags. If you think about a stuntman jumping off a building, if he lands in an airbag, the time over which he slows down is much larger than if he were to just land on the pavement. And so the force is much less, and he survives the fall. If he lands on the pavement, delta t is very small, F is very big, and that large force would injure or kill the stuntman.
What's the matter, John?
I love it.
I don't know, Bill.
Are you into going higher?
Yeah, we're gonna go higher after. This is just a warm-up.
Pistol rolling, got the chaw in the back, pistol rolling. Got the chaw in the back, got the chaw in the back. No, boy, I got some of the pistol rolling. Pistol.
We're on 40. What's doing next?
So we're gonna go double front, half turn, another half turn, another double front.
He's going crazy. This guy is going crazy.
In our first example, we'll look at bouncing occurring. So if an object comes in and bounces off something, its incoming velocity will let the incoming direction be the negative direction. Let's just use as an example an incoming velocity of 3 meters per second, and it bounces off at 2 meters per second. This is a change in velocity of the final minus the initial, or 2 minus negative 3, a change in velocity of 5 meters per second. Then if no bouncing occurs, such as in a completely inelastic collision, we see that our final velocity now is going to be 0. And so our delta velocity is only 3 meters per second. It is less. The change in velocity is less when no bouncing occurs than when bouncing does occur. So up here, if this number is larger, that means our impulse is larger. Our change in momentum is larger, and let's see how this can affect an object.
I have a super ball and a koosh ball. And to show that they're the same mass, I'm going to hang them over a meter stick and use the meter stick as a balance to show that they have the same mass. Hang them over either side and put my finger right in the middle, and you see that it balances, showing that they have equal mass. Okay, so both the koosh ball and the super ball have the same mass. The super ball, of course, will bounce off the block. The koosh ball will not. I will release them from the same height, which the string will be parallel to the floor to let you know they're being released from the same height, and will strike the block. Okay, no bouncing. Bouncing.
Oh, wow.
So a greater impulse with the bouncing as opposed to the not bouncing.